All right. So when we look at different sampling distributions of different sizes, we kind of did that with the Reese's thing. You saw the mean was kind of the same, but the shape of the display was different. Okay, even though they all had similar means, the width changed with the standard deviation. So this is very familiar with what we did in Algebra 2. Okay, the mean of the sampling distribution we're going to call P. Okay, and the standard deviation, remember this is called P hat. Very simple calculation. We take the square root of P times 1 minus P divided by N. So I like to use going to just buy candy. Okay, if you buy candy that costs 35 cents, 0.35, and you pay with $1, your change is going to be 65 cents, 0.65. So we're going to keep doing that calculation. So if P was 0.4, 1 minus P would be 0.6. If P was 0.08, 1 minus P would be 0.92, which is a very simple calculation. And you divide by N. Remember this from last year also. For it to be a good study, a good sample, we have to have two things happen. It's called large count conditions. We're going to take the number of things in our situation times P, again, the 0.35, and that has to be greater than 10. And then we have to take the number times 1 minus P, the change we're getting back, and that has to be greater than 10. All right, so suppose 26% of all high school students in a large school spend about half or more of their earnings on a car. A random sample of 150 students from the school is surveyed. Let P hat, the proportion of students in the sample who spend about half or more of their earnings on a car. So that's going to represent those kids who spend at least that amount. So calculate the mean standard deviation. Okay, very easy for mean. Okay, the mean is just going to be the 0.26. We just write the 26% as a decimal. That's it. And then to figure out the standard deviation, that's our P. So we're going to do square root of 0.26. That's the piece of candy we bought. What's the change we're going to get back? 0.74. And divide it by 150 students. That's the N. And that gives us a standard deviation of 0.04. So our mean is 0.26, our average is 0.26, 26%, with a standard deviation of 0.04. And we're not going to do this the whole thing, but again, if I put 0.26 here, I would go up 0.04, 0.04, 0.04, and subtract 0.04, 0.04, 0.04, like we've been doing. Same thing. Mean, standard deviation. Now, what does that standard deviation mean? It means that 0.04, also known as 4%, deviates from the mean. Okay? The 4%. So that's each little width of standard deviation is going to be 0.04. That's the amount it deviates from the mean. All right. To audit one department of a large corporation, accountant selects a random sample of 80 transactions. Historically, the true proportion of transactions that were more than $1,000 is 0.42, 42%. Would it be appropriate to use a normal distribution model to model the sampling distribution of P hat for a sample size of 80? Well, this is that testing the theory. So we have to do 80, or N, right, times P, which is 0.42, and we're going to do 80 times 0.58. So again, if our piece of candy costs 42 cents, our change is 58 cents. And this is the N times 1 minus P. So what do we get? We get 33.6, and we get 46.4. Both of those are greater than 10. So yes and yes, it would be okay. That would give us a good representation. All we're doing, like I said, we've done this before. You're just taking N times the P and N times the 1 minus P. And as long as they're greater than or equal to 10, we're good to go. Whoops. Nope. Go back. No. Okay, we're actually going to skip this one and come back to it. It's a little simpler doing it on the back one first. Because 4 takes us through step by step. Then we're going to come back and do 3. So, first off, we're going to see if it is justified. So we're going to take our number 300 times our p of 0.32 and our 1 minus p of 0.68. And for some reason, that's silly 400 instead of 300. So 300 times 0.32, still going to work out, equals 96. Bigger than 10, good to go. And 300 times 0.68 is going to be 204, definitely bigger than 10. So we're good to go. So it is justified. What are the mean standard deviation? Simple enough. The mean is going to be 0.32. And the standard deviation is going to be, again, 0.32. That's our candy. Times our change, which is going to be 68 cents, 0.68. Divided by the 300, the number in the simple random sample, and that gives us 0.026, so we'll call that 0.03, which is also 3%. So again, if I was making my normal distribution, 0.32 would be in the middle, and I would go up 0.03 3 times and down 0.03 3 times. Same as we've been doing. So this one is just like the previous one we answered. What does the 0.03 mean? It means 0.03 deviates from the mean. Same, similar answer. 3% deviates from the mean. So if it starts at 32%, it's going to go up 35, 38, 41. That's going to go down, so forth. 29, 26, 23%. Then part D. Now we're going to do what we did earlier last week. This is using our charts. Okay? So it says, what is the probability that this works out that 29% compares with 32%? All right? So that's where we take our calculation of our actual value, 0.29, minus our mean, 0.32, divided by our standard deviation, which we found was 0.03. Actual minus the mean divided by the standard deviation. And that gives us exactly -1. So if we go to our chart, chart A, you don't have to do this, I already looked it up for you. Chart A, and looked up -1, that gives us an area of 0.1587. So that means 15.87% probability that less than 300 will have found full-time employment. There's a typo right here. This should be 29% right here. Okay. So, does the admissions office have a convincing evidence that the proportion of graduates who have full-time employment within 1 month is actually lower than 29%? That's opinion. I mean, you're talking, they have about a 16% probability. So, in other words, what does that mean to you? Do you think it is or not? You have to go with that. You can justify it how you want to justify it. Is 16% enough of a probability? Okay, we're going to go back to do number 3. This will go really quickly. And if the board will work. Okay, so for number 3, we're going to do the same thing. What's our mean? We're going to round it. We're going to do 0.73. Okay? Our SD, our standard deviation, is going to be the square root of 0.73 times 0.27 divided by 400. And that's going to give me 0.02 for standard deviation. So again, 73% plus 2% plus 2% and so forth. Now, this is the one we did last week where we're trying to find between 3 percentage points. So that means we're going to do 0.7 minus 0.73 divided by 0.02. And we're going to do 0.76 minus 0.73 divided by 0.02. And this is where we're going to try and find the area in between. So the area in between is going to be negative 1.5 and 1.5. So that gives us 0.0668 and 0.9332. And when we subtract those, we get 0.8664, or about 87%.